Welcome to the fifth video in our Quantum Computers series. Previously we covered quantum computing basics, designed our first quantum circuit, and encoded it on Qiskit and Google Circ. Check out the updated version on qubit-lab's website, which includes videos, Python code for Google Colab, and more resources. In the first deep dive video, we introduced matrices and explored quantum gates, learning their prerequisites and capabilities with Python examples. Today, we will briefly introduce complex numbers with a focus on quantum computing. Many viewers might be familiar with matrices and vectors from machine learning and AI, but complex numbers are less common in technology. I'll provide a gentle introduction. For more detailed videos on complex numbers for beginners, visit the qubit-lab.ch webpage and leave your comments. Okay, let's start. General qubit states can be described by their probability amplitudes for state 0 and state 1, denoted as alpha and beta. Alpha and beta are complex numbers. This concept will now be explored further. There are several commonly used sets of numbers. The natural numbers include all whole numbers from 0 or 1 to infinity. The integers consist of whole numbers as well as negative numbers. The rational numbers encompass all numbers that can be expressed as fractions, such as 1/2 and 1/3, but do not include irrational numbers like pi or the square root of 2. To include these, we refer to the real numbers, which cover all number types typically encountered in high school mathematics. So far, everything is good. I assume there's no news. Imaginary numbers are multiples of the square root of -1, often denoted as I. As you may recall, real number square roots do not accept negative values. However, imaginary numbers allow for negatives. For more details, check out the complex numbers video on qubit-lab.ch. Complex numbers combine real and imaginary numbers represented as a sum of both parts. A general complex number is written as a plus b times I, where a is the real part and b times I is the imaginary part. Here, I signifies the square root of -1. Complex numbers are visualized on the complex plane, where the x-axis represents the real part and the y-axis represents the imaginary part. Every point on this plane corresponds to a complex number, allowing all complex numbers to be located here. We can calculate with complex numbers. Addition is straightforward. Add the real parts and the imaginary parts separately. It's like adding vectors on a two-dimensional plane. Multiplication involves multiplying terms like polynomials, with I squared switching signs since I squared equals -1. Like points on a plane, complex numbers can use polar coordinates. Polar coordinates use a vector from the origin to the point representing the complex number, defined by its magnitude and phase angle in radians. Using basic trigonometry, we find the real part by multiplying the magnitude by the cosine of the phase, and the imaginary part by multiplying it by the sine of the phase. The complex number c is r times cosine phi plus I times sin phi, which simplifies via Euler's formula to e to the I times phi. In polar coordinates, multiplying two complex numbers involves multiplying their magnitudes and adding their phases. Now, let us examine a special case that is significant for quantum computing. This involves the multiplication of a complex number, such as the probability amplitude of a qubit state vector, by another complex number with a magnitude of 1. Recall that the magnitude of a complex number is the length of the vector originating from the coordinate system's origin. Consequently, all complex numbers with a magnitude of 1 lie on a circle of radius 1 around the origin. On this circle, you will find the real numbers 1 and -1, along with the imaginary numbers I and -I. Additionally, there are numerous other complex numbers not directly on either of the two axes. These numbers can be represented by e to the I times phi, where the magnitude equals 1 and can thus be omitted. For a phase of pi, the resulting number is -1. For 2 pi, we obtain 1, and for pi over 2, the result is I, among others. Now we can change it around. Multiplying a complex number by -1 equals a phase shift of pi. Revisit the multiplication rules for complex numbers in polar coordinates if needed. The magnitude remains constant when multiplied by 1, and the phases are added. Thus, multiplying by -1 shifts the original phase by pi, as -1 is equivalent to e to the I times pi. We can also consider other special cases as shown. Multiplying a complex number by I results in a phase shift of pi over 2. Multiplying by -I results in a phase shift of 3 times pi over 2. Maybe you remember that we said, the Z gate shifts the phase of one component but not of the other. That just means the Z gate shifts the phase of one state vector component by multiplying it by -1, while leaving the other component unchanged. The applied phase shift is equal to pi. Moving on from pure mathematics, we return to qubits. In video 4, it was demonstrated that the probabilities of measuring state 0 or state 1 are determined by the squared absolute values of alpha and beta, respectively. The squared absolute value of a complex number represents its squared magnitude in polar coordinates. Thus, the probabilities of measuring 1 or 0 are independent of the phase of alpha and beta. Only the magnitude is relevant. If you think the phase is generally irrelevant, I must disagree. It may not matter for the measurement, but it is crucial for the prior calculations. As we will see on the next slide, phases are necessary for quantum interference. We now consider a sequence of 2 consecutive Hadamard gates. The Hadamard gate transforms any basis state into a balanced superposition, and when applied a second time, it returns the state to the original basis state. Notably, the Hadamard gate is self-adjoint, meaning it serves as its own inverse. We are aware of the final result. The outcome will match the input. Here are the steps to achieve this. We start with a 0 state vector. The first Hadamard gate creates a balanced plus state. Applying the Hadamard gate again returns us to the 0 state vector. Let's look at the probabilities from the initial state to the interim state between the 2 Hadamard gates. Each item in the matrix of the Hadamard gate is colored. The amber item affects the brown arrow, multiplying the 0 probability amplitude by 1 over the square root of 2, and writing it to the 0 amplitude of the interim state. The green arrow does the same for the 1 amplitude of the interim state. The blue and purple values are ignored, as the amplitude for the 1 basis state is 0 in our example. Next, we'll transition from the interim qubit state to the final state. Both amplitudes are now populated, resulting in more arrows. 2 arrows, brown and blue, arrive at the 0 basis state component. 2 arrows, green and purple, arrive at the 1 basis state amplitude. Results will be added where arrows meet. Let's proceed with the calculations. The process of multiplying a matrix by a vector, while somewhat lengthy, is not inherently complex. Although it may appear cluttered, the underlying principles are straightforward. It involves performing element-wise multiplications followed by summing the results. You may wish to pause here to examine the steps in detail. We now focus on the addition of the pathes. The addition after the first Hadamard transformation has one component always equal to 0. However, the addition following the second Hadamard transformation results in the upper 2 lines, brown and blue, summing to 1, while the lower 2 lines, green and purple, cancel out, resulting in 0. Consider this. Brown and blue waves add up because they share the same phase. This is called constructive interference. Conversely, green and purple paths cancel each other out due to their opposite phases. That means a phase difference of pi. This is destructive interference. What's happening here? The Hadamard gate splits the probability paths. It converts the basis state into an equal superposition, distributing the probability amplitude across both basis states. When applied a second time, it recombines the paths, causing the probability amplitudes to interfere, either constructively, adding up, or destructively, cancelling out, based on the relative phases. We extend the quantum qubit sequence by adding a Z gate between the two Hadamard gates. The Z gate multiplies the first component of a qubit state vector by 1, leaving it unchanged, and multiplies the second component by -1, applying a phase shift of pi to the probability amplitude. As seen in the last video, this sequence acts like an X gate, swapping the alpha and beta of the qubit state vector. How did that happen? By shifting the phase of one component of the qubit state vector, we observed completely new behavior. Let us once more examine the flows, noting that they are similar to the previous ones with an additional intermediary step included in the process. In the calculation we see that the phase shift that swapped the sign of the second amplitude leads now to destructive interference in the upper summation and constructive interference in the lower. The simple phase shift made quite a difference in this case. Here we summarize our learnings. Phase shifts without quantum interference do not affect measurements. Applying a Z gate to a qubit state vector yields the same measurement results as without the Z gate, since no quantum interference occurs. But when a Z gate is placed between two Hadamard gates, the behavior of the gate sequence changes significantly. Key takeaway: to make phase shifts impact the result, you must allow quantum interference. Achieve this by splitting qubit states into probability flows, applying phase changes to selected subflows, and then recombining them for constructive or destructive interference. David Deutsch used this technique in his first quantum algorithm, the Hadamard gate, or a quantum Fourier transform sequence, QFT, on multiple qubits can split these probability flows. Here's a brief summary of what we learned in this video. We explored complex numbers, extending real numbers into a second dimension. We studied their polar form for quantum calculations and noted that the phase represents the extra dimension in polar form. We examined phases and found that for measuring a qubit state, the phases of the probability amplitudes are irrelevant. However, for previous calculations, the phases enable quantum interference to occur, which is a crucial feature of quantum computers. Classical computers, in contrast, operate only with zeros and ones, without phases or signs. To build efficient quantum algorithms, enable quantum interference by splitting probability flows, modifying phases, and recombining them for constructive and destructive interference. Use Hadamard gates or quantum Fourier transform for splitting probability flows, as demonstrated by David Deutsch in his algorithm. This was video 5. Well done. You should be proud of completing it. It's challenging. I hope you are beginning to experience the unique appeal of quantum computing. In the next video, we will discuss multi-qubit systems, entanglement, and phase kickback. Meanwhile, visit the qubit-lab homepage at qubit-lab.ch for all videos, Python code, and additional resources. Hope to see you again. Have a great day.